So now we will see the notion of gradient boosting, which is a family of algorithms based on boosting. The idea is to combine the boosting idea that we saw with ADA boost and boosting with gradient descent. So we are making gradient boosting by making a sequential construction of an ensemble where we aim at minimizing the error residual with a gradient descent. So the formalization is to say we have a big fj of x function, which represents the ensemble model at iteration j. So typically we have this as a linear combination of all classifiers from iteration I1 to j. And this is with a weight, the gamma L, that is making somehow the weighting for each of the models we have so far. So from this, we have a recurrent form. We can see that this kind of summation form can be expressed as a recurrent form where the current model is in fact the model of the previous step plus gamma j hj, which represent the classifier we just obtained for that the current iteration. And as such, the residual that we are using here is the remaining of the error. So basically, it's the error, the difference between the target value. So this is what we want as target value versus the output provided by the ensemble at the current iteration. So this difference is the residual, the residual of the error residual that we have that we want to minimize by gradient descent. And so the gradient descent can be applied with, for example, quadratic error. So we have the mean square error here that is, or the square error here that we are using. So this is a difference between the target for each sample from 1 to n, and the output provided by the ensemble at the current j step. So we have this difference squared. We have the sum of all differences, and we divide it by 1/2. The derivative of that, so if we do gradient descent, we have minus the partial derivative of the error over the current ensemble, and that is corresponding from this equation here directly to the R, the real output that we want, minus the ensemble output. And this gives us the residual for the ensemble at step j with sample I, data sample I, xi. And the way to see this is with that diagram. So we have the initial samples here. We get through the learning of a decision tree, for example. That is the basic classifier. And then we have some output. And this output, from this output, we compute the residual, which is a difference between, for each sample, the output obtained for that sample versus for starting with the single model output. And as we go along the different iteration, we will look at the difference between the target and the ensemble output that we obtain. And in the end, we can assume that this residual goes to something really small, and then we have a really good fitting of the data we have to process here. And at each step, we learn one model that is trained from the residual in order to achieve the final outcome, the final output, which should be as close as possible to the real samples and the target R that we have for each of these training samples. So the decision function is basically a linear model where we will combine every classifier through a weighting. So it's a weighted vote. And we build this incrementally. So we just start initially with a basic starting point model. And from that model, we learn each model from the previous one, basically by looking at the output of the previous output plus what we have as output here for the sample X by finding the H. So we are looking to obtain the model Hj that is minimizing this loss here. So basically we are minimizing the residual error here. So try to find the Hj that will minimize this error and use that as the new model for the new iteration. So usually if we are able to deal with models that are differentiable functions, so we can directly do gradient descent over that. So we do the gradient descent according to the loss function that we are using here, and that is making an update for our model to get a new model by this gradient descent. So, and this gradient descent is basically leading us to the H model. For the discrete case, H is then finite, so we choose the nearest model in our set of possible models that is the closest to the gradient. So this is a kind of heuristics, and we'll try to find in our set of possible models the one that fits the best the gradient that is allowing us to minimize the residual error among all the possible choices that we have. This is not necessarily I would say, provide us with the global optimum that is an heuristic that is functioning well enough to what we need. So the gradient boosting algorithm looks like that. We initialize with constant values. Then for each classifier, we compute the pseudo-residual. This is obtained from gradient descent. And then we train a classifier on this. So the classifier we obtain to this iteration is made from that pseudo-residual. And over that, we will compute the weights by optimizing. So we try to find the weight gamma j that will be the one that will get us with the best possible performance over the addition of the new model in the ensemble. And from that, we update the ensemble with the new model H and the new weights gamma that is corresponding to that iteration. We can do that with decision trees. And the idea is that in decision trees, we are dividing the input space in regions, and each region is associated to a leaf and a decision. So we can see this as a way to go down in a tree. So the BLJ is the value predicted in that region. So we have some region RLJ here. And I would say this is coming from the activation function, so the indicator function. This indicator function return 1 if X is in the region and 0 otherwise. And as we are in that region, so if we go down to a leaf and we see, yeah, this is the leaf that corresponds to the sample, input sample, then we assign the sample to the value BLJ. This is basically going down in the tree. So we have this tree here, for example, and we say, okay, we have to go down and this is the final leaf here. So it means that in that leaf, the indicator is 1, and for the other leaves, the indicator is 0. And so we are in that leaf, and we assign then the sample X that gets from the root to there to the value BLJ that is associated with that leaf. In the base version of gradient boosting, the gamma j is constant, so we just don't change that necessarily. It's something that we can just keep constant. In Friedman proposal for true gradient boosting, we have a different gamma LJ per region, so it kind of eliminates the BLJ. So that's something we can use inside our model, and we can just simply say that we will do this training of a tree according to the fact that the decision H is basically to go down in the tree, and we have in the leaf the gamma LJ that is corresponding to the value that we can use. So that's a different way to express gradient boosting through the use of decision trees. So there are some variants of gradient boosting. We have the XGBoost approach, which is kind of commonly known. The idea of XGBoost is that we are making use of a more complete regularization to control overfit. So it is made to scale. So this is basically an approach that can scale to billion of samples, and it works well, and that's a context where we can use many computers to compute it. It allows the use of problem-specific objective functions, some evaluation criteria. So that's kind of customizable approach. We have a lighter version, which is called Light GBM, which is efficient in fast and large data set, and reduce significantly the use of memory. So it can handle large data sets, large feature sets, which is another well-known and used implementation of gradient boosting.